Good afternoon, everyone. My name is Hannah Williams, and I will be presenting my research on methylation and DNA mismatch repair in the yeast Saccharomyces cerevisiae. Defects in DNA mismatch repair cause Lynch syndrome, which is a syndrome that is composed of various cancers such as rectum, colon, and ovarian. These cancers result from mutations in mismatch repair genes such as MSH2, MSH6, MLH1, and PMS2. And they also result from mutations and factors involved in recruiting the mismatch repair proteins to the DNA. The DNA mismatch repair process begins with a mismatch insertion or deletion in the DNA during replication. Next, MUT-S alpha, which is composed of MSH6 and MSH2, is recruited to the DNA. And after that, other factors are recruited, and the mispaired base is replaced with the correct one, and the DNA is resynthesized. Because MUT-S alpha is a DNA binding protein, it needs to be able to access the DNA. So nucleosomes ahead of the fork, the replication fork, and behind the replication fork are disassembled to give MUT-S alpha better access. Therefore, there must be some coordination with complexes that modify chromatin to facilitate access to the DNA by MUT-S alpha. So chromosomes are composed of histones, and histones can be modified in various ways, such as methylation, which is what my project focuses on. Histone methylation is the addition of a methyl group, and histone demethylation is the removal of a methyl group. And specifically in humans, histone H3K36 is involved in the recruitment of MUT-S alpha. However, how MUT-S alpha recruitment occurs in yeast is poorly understood. So my project goal is to examine the role of enzymes that modify histones in yeast MMR and to alter the expression levels of genes encoding enzymes that modify the chromatin landscape and determine the effect on MMR. So what I did was target the SET1 and JHD2 gene. These genes modify the histones through methylation. SET1 is a histone methyltransferase, and JHD2 is a histone demethylase, and both of these genes target H3K4, which is histone 3 lysine 4. My hypothesis is that disrupting the regulation of H3K4 trimethylation will result in loss of MUT-S alpha recruitment and increased mutation frequency. My experimental approach includes the deletion of JHD2 and SET1 and the overexpression of JHD2 and SET1. I then performed MMR assays, and next I will test sensitivity to DNA damaging agents. So as previously stated, first I deleted the genes through transform PCR product into yeast strains, which I then I planned to replace the gene with URA3 by homologous recombination. This shows the PCR implication of URA3 with flanking homology of genes. As you can see, some of these didn't show up through the gel electrophoresis. And this process in general just took way too long and was a little complicated. So we just ended up buying the strains that already had the genes deleted. So next, the strains were transformed with plasmid RS413, which contains the His3 genes. And then these strains were selected on plates lacking lacking histidine. And next, I will test MMR function with the CAN assay. So cannabinine is an analog of arginine, and in MMR proficient cells, mutations are repaired in the CAN1 gene, which and the CAN1 gene encodes for a permease, which allows cannabinine to enter the cell. Once the cannabinine enters the cell, it replaces arginine, which disrupts protein synthesis and leaves the cell dead. So it doesn't allow the cell to grow, any of the cells to grow. In MMR deficient cells, mutations are not repaired in the CAN1 gene. So the CAN1 permease isn't formed properly. Therefore, cannabinine cannot enter the cell, so the cells are able to grow properly. Future directions with my projects include performing the CAN assay with JHD2 and SET1 mutants. And we also have strains that overexpress JHD2 and SET1. So the MMR function of the overexpressed JHD2 and SET1 genes will also be tested to determine if they have defects in MMR. Any questions? Thank you.